Hey guys, Mr. Lum again, and here is trial KSP worksheet. You should have this on Microsoft Teams. Download it, try to do it, and if you get stuck on a problem, refer to this video for your solution guide. Anyways, things that we should have when we do this is we should have our data booklet, something like this, okay? And so we can see all these kinds of numbers because they're going to be really important for when we answer these questions. Okay, going back to here, Chemistry 12, trial KSP. So I'm going to jump into it. At a certain temperature, the molar solubility of zinc oxide, zinc hydroxide is 1.65 times 10 to the negative 5 molar. Write the solubility equilibrium for this thing right here. So it's going to start us off with a nice easy question, and it's ZnOH2 solid. Sometimes I'm bad about writing these things. 2 plus OH minus. There is 2 OHs there, so we got to balance this equation and write the 2 right there. Okay, so there is our equilibrium equation. Write the KSP expression. Since this is a solid, it does not go into our KSP expression. So KSP is going to be equal to the products multiplied together. So zinc 2 plus times OH minus. Since there's that 2 in front, we get a squared right there. And calculate the KSP for ZnOH2. Now, it says the solubility for this thing is 1.65 times 10 to the minus 5. So if this is 1.65 times 10 to the minus 5, that is the concentration of zinc hydroxide. Since this is a 1-to-1 ratio, this is also going to be 1.65 times 10 to the minus 5. Now, this number right here is going to be twice as much. The hydroxide is going to be twice as much because it's a 1-to-1 to 2 ratio. So 1.65 times 2 is equal to 3.30. So this is going to be 3.30 times 10 to the negative 5. Okay. And so that's the molarity of these things. So calculate the KSP. We're going to plug these numbers right here into our KSP expression. So KSP equals zinc concentration, which happens to be 1.65 times 10 to the minus 5 times 3.30 times 10 to the minus 5, and that's squared. So I'm going to put that into my calculator, and I'm going to go 1.65 times 10 to the minus 5 times 3.3 times 10 to the minus 5 squared equals times. So my answer for my KSP expression is 1.796 or 1.8 times 10 to the minus 14. Now, as we know, KSP does not have any units, so we're just going to leave it like that right there. Technically speaking, if I'm going to be like the number that came in my calculator was 1.79685 times 10 to the minus 14. Now, technically speaking, these numbers right here are all 3 sig figs. So my answer should be 3 sig figs. KSP does have significant figures attached to it. So I should be writing 3 sig figs. This number is going to round up. So I should be writing 1.80 times 10 to the negative 14. Okay, so that's the answer to our first one. Will a precipitate form if 100 mils of lead nitrate or lead 2 nitrate solution is added to another 100 mils of that concentration of magnesium sulfate solution? Show all the calculations excluding the trial KSP. So when it says like that trial KSP thing there, and I'm going to be looking up the real KSP. What I'm going to actually do before I look up the real KSP is I should kind of have an idea of what precipitate is going to be forming. So if I have PB NO3 what's going to happen is that it's going to combine with magnesium sulfate, and it's going to turn into MgNO3 and PB SO4. This right here is our precipitate. So that's what we're interested in. Everything else that is not part of PbSO4 is just going to be a spectator. So my KSP expression should actually be PbSO4, Pb2 plus SO4 2 minus. Solid, aqueous, and aqueous. So now I'm going to now that I have my formula for my KSP expression, I can even write a KSP expression right here since it's just 1-to-1-to-1 ratio. KSP is going to be equal to the concentration of Pb2 plus times the concentration of SO4 2 minus. And if I'm now going to look up on my data booklet here, let's look it up together actually. So let's go look up lead 2 sulfate, and we see that it is 1.8 times 10 to the negative 8. So we're going to minimize that. And so real KSP, where should I write that? Let's say real KSP is 1.8 times 10 to the negative 8. So that's my real KSP right here. Okay. Now I'm going to look up the trial KSP, and it gives me some concentrations of this stuff. Now this is a little bit weird. It says 100 mils of this right here is added to 100 mils of that stuff right there. So if it gave me different volumes of this liquid, then it's a little bit annoying. You'd have to do some CI/VI stuff, and you should still be doing some CI/VI equals CF/VF to find the new concentration of your lead and the new concentration of your sulfate. So you should be doing all that kind of stuff. But this question is kind of really nice since they are equal volumes of this. What it actually does, it takes the concentration of lead, and since you're just doubling the solution, that means since you double the volume, you half the concentration. So the new concentration of this lead right here is going to be half of what it originally is here. So it's going to be 0.5 times 10 to the minus 3 is going to be the concentration of that PB right there. So that is the concentration of the lead, 0.5 times 10 to the negative 3, or you can say 5.0 times 10 to the negative 2. So that's going to be the concentration of lead right there. Again, this one's also being halved as well, this sulfate right here. So normally it was 2 times 10 to the negative 3. Since we doubled the solution, that means it's going to half the concentration. Okay, so this new concentration is now going to be 1.0 times 10 to the minus 3, and that's going to be the new concentration of sulfate right there. So what this is going to now look like when I turn this into a formula is that now that we have our new concentration, it's going to be 0.5 times 10 to the minus 3, and you can write 5.0 times 10 to the minus 2, same number, and you're going to times that by 1.0 times 10 to the minus 3. That's what we said. So, and by the way, I should be writing trial KSP. So my new trial KSP is going to be, well, I take these two numbers and multiply them together. So I'm going to go 0.5 times 10 to the minus 3 times 1 times 10 to the minus 3. And that equals 5 times 10 to the minus 7. 5, well, we got 2 sig figs, so it's going to be 5.0 times 10 to the minus 7. And so that is our trial KSP. So the question is not asking what is the trial KSP. Well, it kind of asks what's trial KSP. But now what we have to do is we have to compare trial KSP to real KSP. Okay, so what we see is trial KSP. Trial KSP is greater than real KSP. So since trial KSP is greater than real KSP, that means there are too many ions in solution. That means these concentrations are too big, okay? That means they're too large, and that means there's too many ions in solution. So since there's too many ions in solution, these numbers are too big, is going to want to shift to the left direction there. So since these numbers are too big, they are going to want to become smaller in order to become more like real KSP. So in other words, since it's going to be shifting to the left, that means a precipitate forms. Okay, so in chapter 2, we talked about trial KEQ and real KEQ. And trial KEQ, we said if trial KEQ is like this, it'll shift to the right. If trial KEQ is like that, it'll shift to the left. Trial KSP is no different. But since trial KSP is larger, it's going to be shifting to the left. And that means shifting to the left means it's going to be forming a precipitate. Okay. Will a precipitate form if we have 2.5 grams of sodium sulfate is added to 60 mils of a 2 times 10 to the negative 4 molar solution of barium chloride? So again, let's figure out what kind of precipitates we're going to be getting. So we have Na2SO4 plus BaCl2. That's going to double replacement reaction. So that's going to be BaSO4 plus NaCl. So this right here is our precipitate. We could figure that out by looking up at this table right here and seeing BaSO4 is a precipitate. So we look up SO4, we see Ba right there, and we see BaSO4 precipitate formed. Okay, so that's our precipitate. So our KSP thing is going to be, say, BaSO4, Ba2 plus SO4 2 minus. And now we need to figure out the concentrations of everything. So first off, it tells us the concentration of Ba. Ba is going to have a concentration of 2.0 times 10 to the negative 4. Now we need to find the concentration of this SO4. So first off, it says to us we have 2.5 grams of this thing right here. So I'm going to go 2.50 grams. I'm going to convert this into moles by going 1 mole is equal to, so Na is 23. There's 2 of them, so it's going to be another 23 plus 23 plus, and I believe sulfur is like 32.1, I believe. Yep, it is. I had a periodic table next to me. So it's 32.1 for sulfur. And oxygen is 16. 16 times 4 is 64. And so when I'm going to add all these numbers up to find the molar mass of sodium sulfate, so 23 plus 23 is 56 plus 32.1 plus 64 equals, and I get 152.1. 152.1. And then we're going to go 2.5 grams. So 2.5 divided by 152.1 equals, and I get 0.016 moles. I don't want moles. I want molarity. So I'm going to divide by our milliliters. So divide by 0.06 equals, and I get the concentration of 0.27. 2739 or 274 molarity. Okay. I'm going to look up real KSP. Real KSP is, let's look that up together. We say barium sulfate is 1.1 times 10 to the minus 10. It's right there. So real KSP is 1.1 times 10 to the minus 10. Just like that. Now I'm going to calculate trial KSP. So trial KSP equals BA2 plus SO4 2 minus. Trial KSP equals 2 times 10 to the minus 4. I should have wrote 2.0 times 0.274. I can already see that this number is going to be way bigger. Trial KSP equals 2 times 10 to the minus 4 times 0.274 equals, I get 5.48 and 48 times 10 to the minus 5. So that's my trial KSP, or if I'm using proper sig figs, 5.5 times 10 to the minus 5. So that's my answer right here. Trial KSP is way larger. Trial KSP is much bigger than real KSP. So therefore, precipitate forms. Okay, last question right here, and we'll call it a day. Anyways, calculate the maximum concentration of fluoride ions possible in a solution which has this in there. So first off, KSP for strontium fluoride is, let's look that up together. Strontium fluoride is 4.3 times 10 to the minus 9. 4.3 times 10 to the minus 9. Now, and that's for SRF2, and that will be SR2 plus 2F minus. Okay, so KSP expression is going to be equaling to concentration of SR times the concentration of F minus squared. Okay, that is the tricky part right here. Now I'm going to plug in some of my numbers right here. So it's going to be 4.3 times 10 to the minus 9 equals concentration of SR, which is 5.0 times 10 to the minus 3 times F minus squared. I'm going to go plug into my calculator. 4.3 times 10 to the minus 9 divided by 5 times 10 to the minus 3 equals, okay, and I get 8.6 times 10 to the minus 7 equals concentration of fluorine squared. I have that squared there, so I need to take the square root of this number. So I'm going to go square root this number equals, 8 points. Syntax error, my calculator said, because I didn't type it in right. Minus 7 equals, and I get 9.27. So just the concentration of fluorine equals 9.27 or 9.3 times 10 to the minus 4 molarity. Okay. And that's our answer right there. I'll post this video for you so that you can see how to do the worksheet in case you have any questions about it. And as always, if you have any questions, please feel free to message me on Microsoft Teams.